So I want to show you something quite extraordinary. You can see I have I've got a light bulb over there, and it's sending rays of light across the room at this small hole in this screen. What is happening behind the screen is this. The light is eventually hitting this small lens. But what happens after that is the light goes through the lens and then projects onto the screen behind. And can you see there is the image of the light bulb? So this has formed an image on the screen, projected, as you can see. Now, we call this sort of image a real image because it looks like it's just there. I could literally touch it. It appears to be on the screen. And this isn't the only kind of image that we might get. So here, in the boys' bathroom, you can see that there is a mirror there. What you can see is there's no image forming on the wall behind me. There's no projection of what the mirror is doing. There is a reflected version of me. It's just over there. I can only see the image of me by looking through the optics. That is what is known as a virtual image. This concave lens does not form an image on the screen, not at any distance. However, when we look through it, what we can see is an image has formed of the light bulb and the white screen behind it. But notice how small it looks. If we were to believe the image that was coming through this lens, then what we would do is we would think that the light source was probably 5 meters away, when actually it's 2 meters away. This virtual image has made us believe the source of the light is in a different place to where we actually see it. Check out this optical illusion. It looks very much like I could just reach and pick up that little red ball that is sitting on top. But what I find is that it's not actually there. Why can't I grab it? I can't even touch it. It's just not there. And that's because it isn't there. It is an optical illusion. What is happening here is that there is a curved mirror underneath. And that curved mirror is making the red bead, which is actually right down here, right down there. I can't just touch it. It's making an image of it appear up here, not in the place where it actually is. This is also a virtual image. What we can see with a convex lens is that not only will it produce a real image on a screen, but that if you actually look through it, you will see a virtual image too. Convex lenses are capable of creating both a real image and a virtual image, whereas a concave lens can only produce a virtual image. So for us to fully understand this, we need to draw a ray diagram. Now, these are quite complicated, but hopefully you'll understand. The first thing I'm going to draw is just a line representing, well, the axis, the principal axis through my experiment, but I'm not drawing it through the middle. I'm drawing it like this. And what I'm going to draw on this is just another line to represent where my lens is going to be. This just helps set up what I'm trying to display. And I'm going to freehand draw a nice convex lens here on that point there. Now I'm definitely going to have a screen on this side, so I need you to imagine this is where my real image is going to be projected to. Now if I draw a person over here, then the light that is coming from this person is going to go through the lens and it's going to form a real image. How do we draw it? Well, what we do is we choose 2 points. The first point is we'll choose the top of the person's head up here. And we will consider 2 rays of light from that person's head. So the first ray of light travels on a straight line over to the lens. It is then refracted quite severely because of the curvature of the lens and ends up going over there. Can you see? Now a ray of light from the foot of the person would go in a straight line. Well, it's probably not helpful to draw it there. Let's draw it about here from the knee. And you can see that what's happening is that too would be refracted through the lens and eventually would end up over there. And now what's incredible is it has crossed over in flight. But this was the principal focus, remember? Where the rays are all converged by the convex lens. It's called the principal focus. But what we're looking at is not what happens at the principal focus, but what happens if the light then hits a screen beyond the principal focus. Well, the next thing to do is to imagine another ray of light coming from the top of the person's head to another point in the wave. It is not refracted nearly so much, just probably a little bit, and it ends up back over here again. So that what basically has happened is that though it was refracted as well, it still ended up in the same place, which means that the light from this point, all of it, ended just there. And the same with any other ray of light travelling from the knee, so any other random angle, what we find is that it is refracted not quite as much as before, but it still ends up in the same place as all of the light from the knee. What's going on here is all of the light from the head is ending up in one place, all of the light from the knee is ending up in one place, and so basically what you're going to get is you're going to get a version of this person, this forming an image on this screen. Now, notice two things. First of all, because the rays of light converged, went through the point of focus and then diverged again, it has flipped the image upside down. And indeed, whenever we see a real image forming, the image is always projected upside down. Did you notice that earlier in the video? And second of all, it is smaller. In this particular case, it has made the real image apparently smaller than the object that has caused the image. Now this is exactly how our eyes work. Our eyes contain a lens just like this, and what is projected onto the back of our eye, the retina, is an upside down real image of the world that we can see. Our brains untangles this information, flips it the right way up, and then it is interpreted as our sight. And so this is how a real image forms. So how does a virtual image form? So just as before, we have our lens. And we're going to go with a convex lens. And what we saw when we looked through the lens at the picture of Einstein was that when you look through it, there is an object can appear in the lens and normally further away than the actual object you're looking at. So what is the ray diagram for this setup? Imagine that there is a picture of Einstein. Here's his moustache. Right, and it is here, and to your eye, and I want to draw an observer's eye here, looking through the lens. What has happened to the rays of light? Well, let's draw them on. The ray of light coming from the top of Einstein's head has been refracted slightly and will come to focus in the person's eye. The rays of light from the bottom of Einstein will refract slightly and also come to focus like that. But now you need to imagine how that actually looks, because what it appears is that that ray of light has not come from there, it actually looks like that ray of light has come from up here. And this ray of light looks like it has come from up there. And so for this particular ray diagram, so that is the rays going in, still going in there, it looks like there is a giant Einstein much further away than in reality. So in this example, this virtual image appears the right way up and in a different place to where the object actually is. So we have an image. What are the three things that we could describe about the image? Is it larger or smaller than the original object? Has the lens magnified it? Is it inverted, like those real images? Is it upside down? And is it a real image, which means it can be projected onto a screen, or is it a virtual image you can only see by looking through the optics itself? These are the three main things that we can say about an image. So what if I wanted to find the distance that a real image would appear as projected from a convex lens from an object? Well, we can do it with a ray diagram. How I'm going to do it is I've got three pieces of paper that are basically attached together. The very first thing that I'm going to draw here with my large ruler is the principal axis, and it goes all the way along. In fact, I've got to go round to finish it off. This is the centre line through our lens. And we call that the principal axis. I'm going to write that down, principal axis. And we're going to need a lens. So I'm going to put my lens over here, about there maybe, on the join. So how do we represent a lens? I've in the past told you to draw around it. We now get a little bit more sophisticated. Instead of drawing around it, we're going to represent it as a vertical line on the paper, and hopefully it should be exactly at 90 degrees to the principal axis, otherwise it'll all go wrong. So this line with the black arrow at the top and the bottom represents where our lens will sit, and we'll stick it there. The next thing is we need an object whose image is going to appear over there. So as always, it's going to be Rapunzel. So we sit Rapunzel over here, and we're going to look at the image of her head alone. So we're lining the principal axis up with her neck. And I'm curious about the light emerging from the position at the top of her head. Where does that go? Now, what we found before on the blackboard was that the light from one place has to arrive all in one place for an image to form at that place. So I can take Rapunzel out of the way, and I can actually replace Rapunzel and represent Rapunzel with a vertical line with a thing on the top, and we call that the object. Sorry, Rapunzel. And this is the lens just here. Now I'll put Rapunzel back just so that it's really clear what I'm doing here. I've also got here my laser. So I'll turn my laser on, and hopefully it will come on. Is it on? The laser's not on. What's happened to it? There we go. I have my laser beam line nice and clear, nice and crisp. And there we go. So the first thing I'm going to do is I'm going to examine what is going to happen to a parallel ray to the principal axis. So this ray, you can see, is parallel to start with. And so I can draw on my X marks both here and after it has gone through the lens. Now I've drawn on my X's, I take away everything. I take Rapunzel, I take away the lens, I take away the laser. And I use my ruler again to now join those dots. So the ray of light comes from the top of Rapunzel's head until it hits the centre of the lens. It then refracts and it goes over here somewhere. Okay, so get it right. And I don't know where I need to draw it to. It is going over there. So now let's put Rapunzel back in situ, put our lens back, and the second thing we need to now examine is what happens to another ray of light. So another ray of light, in this case, is the ray of light that goes from the top of Rapunzel's head to the middle point of the lens. Okay, so it's going from the top of her head to the middle point of the lens, like that. So this ray of light is going here and here, and here, and here. So we now remove everything once more, take it away, take Rapunzel away. We join those lines that go from the object to the centre of the lens. Then pay very close attention to where those rays of light go next. Okay, so they're going to go all the way over here. And if we just make sure that our line from before continues in the same way, what you'll notice is there is a convergence point just here. This is the point where the real image will form. So here we can label the real image. And what could we say about this real image? Well, first of all, the top of her head is now at the bottom and her neck is at the top. So to start with, it is inverted. The second thing is that her image in this case is 8 centimetres compared to her actual head, which is 4.5 centimetres. So her image is larger. It has magnified her head. This distance here from the lens to the image is called the image distance. This distance here is called the object distance. There are one or two more things we can add to this diagram. This point here, where the parallel ray of light crossed the principal axis, is called the principal focus, and it is at F. Now, if we look, it is 21.8, that side. If we found the other side, that we could also mark this point, the equivalent distance on this side of the lens. Now, where the object is relating to this distance, which is equivalent to the length of the focal length, the length to the principal focus, that has a big impact on what is going to happen to the image over there. So with the ray diagram, we can find out where an image will appear. But how can we tell from a ray diagram whether or not the image is going to be enlarged or whether or not it's going to be diminished? Well, what we can do is consider this. Here are a set of principal axes and a set of lenses. These are all separate examples. In each of these situations, the focal point of the lens, the principal focus, is given as F. Now, if I imagine that this point here is 2F, if I have an object which sits just here at 2F, and it is, I don't know, this big, so Rapunzel's head once more, the rays of light, well, the first one going parallel will hit the top of the lens, go through the focal point, like this. The ray of light going from the bottom through this point will actually carry straight on. If you consider that it hasn't really changed direction, because any refraction here has been undone there. It means that the image of this object, which is formed here at 2 times f again, is the same size as the original. So when the original is placed at 2f, then the image is the same size as the original. But what if we had a different example? Well, if I now put my object closer than 2f, for example just here, like in the example where I was actually measuring Rapunzel's head, then what I would find is the following: the ray of light going parallel like this, and then through that axis down there. That always goes through the focal point, that top one, and the bottom one that goes through here always goes straight, and you can see that they're converging over here somewhere. And so what you can see is, in this case, the image is massive. I mean, it's actually crept onto this little diagram, it's so big. But what you can see is the image in this case is larger than the object, because the object was closer than 2 times the focal length. So it has enlarged itself, and that is what we found with Rapunzel. What happens if we bring the object closer than f? Crazy things. So if I imagine my object is, I'm not going to draw it as big this time, otherwise it would get out of hand, but imagine that this is my object and it is so close to the actual lens itself. What is going to happen with the lens? Well, the first one is going to go parallel like this, and then go through the focal point like this. But then the second one is going to go through the centre, and as you can see, it is divergent. It is never coming together as an image on this side. What instead is happening is it is making, if you were on this side and looking through it this way, then what you would then see is, if we trace these back, going back this way, looking through this backwards would give the appearance that the image was behind and larger. So what you can see here is, with a convex lens, if the object gets within 1 focal length of the lens, then what happens is no longer is a real image produced, but a virtual one. But you won't see it from this side of the lens. You will have to observe it from this side. And that is why a convex lens is both capable of seeing or projecting a real image, as well as, when you look through it, be able to produce a virtual image. We have all seen this before, using a magnifying glass. So what you can see is, when the object, here Rapunzel, is within 1 focal length for this lens, then what we see is a enlarged virtual image. It looks absolutely huge compared to before. And so that's that. But as we pull the magnifying glass away, we hit 1f, and no longer does it produce a virtual image, but now would be producing a real image that is inverted. And that real image is now falling on my lens of my camera. There is one last thing: magnification. Whether or not an image has been produced that is larger or smaller than the original, well, there is a formula that can help work this out. It is equal to the image height divided by the object height. So, for example, if we look at some of these, well, the image height here is 9 centimeters, and the object height is 9 centimeters. 9 divided by 9 is equal to 1. It has a times 1 magnification. The image is the same size as the object. It hasn't magnified or diminished it at all. What about this great big thing? Well, the image height is 31.5, say, 31.5 centimeters, and the object height is about 10 centimeters. And so therefore, the image of 31.5 divided by 10 is going to equal 3.15. It has made, in this case, the image 3 times larger, magnification of times 3. Here, even though this is a virtual image, we can still apply the same formula. The object height is 5 centimeters, and the virtual image height is 10 centimeters. So this would be 10 divided by 5, which is equal to 2. So this has magnified it by a factor of 2.